Welcome to the Windows 101 lecture. My name is Owen Redwood. I'm with Hack All the Things, and this lecture is part of the Offensive Computer Security Open Courseware. This lecture is going to cover the fundamentals of memory handling, the Windows registry, which is essentially the nerve center of the Windows operating system and platforms, the Windows boot sequence, other details of the Windows architecture like the PE file format, and we're going to cover Windows security topics, the Windows domain and network security topics, as well as rootkits. Some of the books that I've used over the years to build these lectures are worth noting. The Windows Internal series, I think it might be on 7 or 8 right now, is essential to doing any Windows system administration or security work. Similarly, learning the internals of an operating system, or rather a target, is very useful to use resources that have an offensive mindset. Now, towards that, I would recommend the rootkit arsenal as well as designing BSD rootkits. Although BSD rootkits is not Windows specific, it certainly has many parallels that and insights to offer that are universal across kernel exploitation. So let's start with the fundamentals for a single process and how its memory is handled, and then dive down deep. So each process gets a virtual address space. The size total will differ depending on if it's 32-bit or 64-bit, and is typically not shared between other processes by default. There's within it a partition for the process itself, operating typically in user land, and then a separate partition for system level functionality, or rather kernel land. So let's dive down and explore how these partitions are enforced, because we don't want user land activities to access the resources of the kernel land. That's typically a security problem. So this enforcement is typically done at the hardware level, either by segmentation and or paging in an operating system. Windows here uses both, but typically uses paging more often. Paging is simply dividing memory into small partitions that are each the same size and grouping these partitions into page frames. Each page frame may have a specific use, and there may be a number of page frames per virtual address space. In other words, per process. So when a process is loaded, it gets divided into all these pages, and these pages are then all loaded into the frames. The advantages to this are it's transparent to the programmer. He or she doesn't have to do any extra overhead to accommodate or facilitate this. There's no separate protection, there's no separate compiling of each page frame, and there's no shared code that has to be managed or worried about. Segmentation is different. Segment sizes can be completely variable, and instead of having the partitions be singular chunks or pages that are all the same size, you can allocate it for whatever size you need. So that involves programmer overhead. They have to be involved to dictate what they need in terms of size for the either inputs or temporary space and calculations used by the process itself. And they can have varying amounts of protections. They can each have their individual protections or have shared permissions enabled for multiple processes to interact with them. A common term that almost anyone taking this class should be familiar with is a term called segmentation faults. And these occur whenever data is read or written in a manner that is prohibited by the address space permissions or the segment permissions. It's also more commonly known or referred to as seg faults in general. So, the Windows NT family spans across Windows 2000 to Windows 8 and now more recently Windows 10. And each of these use some core layers and or components of the Windows architecture, most commonly NTDLL.dll, as well as the Win32 API. They all do Windows NT domains similarly, as well as workgroups, and typically have some Active Directory features. So Windows has always been a multi-tier design with multiple layers going on in kernel space as well as user land. It's mostly implemented in C and C++ with the lower level stuff in the kernel happening at the assembly level. And the hardware abstraction layer exists to kind of make peripherals and third-party hardware and drivers more universally plug and play, and it does that by isolating chipset dependencies and abstracting it all out. And the operating system has been designed to support multiple architectures, MIPS, ARM, x86, etc. But as a security note, from each Windows version to the next, there's typically a large amount of backwards compatibility going on. There's been historically many vulnerabilities that have been inherited from one OS version to another, and backwards compatibility in general is typically just regarded as the bane of security. It typically, once it becomes legacy, no security, code auditing, or maintenance occurs in these components. They just get inherited into the successor and left as is, which means that any vulnerabilities that exist within them, even if they haven't been found yet, then become a problem in the successor targets, or in this case, operating systems. So let's cover some historical vulnerabilities attributed to backwards compatibility issues. Probably the most notable is NTLM, aka Landman Password Hash Format, which is notorious for being super easy to crack. Next would be the Windows meta file exploitation problem. Windows meta files allow you to essentially make images like JPEGs and GIFs actually also be interpreted as EXEs, so getting a target victim to double click on an image might instead run an executable should they have downloaded it. The PE file format over the years has had several problems that have been exploited by malware. SNMP, which is Simple Network Management Protocol, but I also teach it as Security is Not My Problem Protocol, has decades of vulnerabilities and attacks associated with it. It is a huge information leak in even the most benign case. The Xbox One console that came out recently had it was almost a day one vulnerability that, as a prank, I guess, people who hated Xbox went about bricking. It was, I think, by means of social engineering and tricking people into doing this on the console via a backwards compatible feature. I forget exactly the specifics, but using it the wrong way would brick the Xbox, and that was something that got a lot of press. But there are other more serious examples that lead to remote code execution on target machines, like CVE 2014-6332, which is a Internet Explorer 11 exploit and sandbox escape to direct God mode on the target machine. And God mode is a specific term within Windows vernacular for essentially super user. Next is the JASBug or Jasberg vulnerability that was active for 15 years, where the prior one was 19 years across Windows platforms. This one was more core to the Windows OS itself. It required Microsoft to re-engineer several key components of the operating system and to add new features in order to fix this. But anyways, there's a lot of reasons for Windows having so many perceived security problems, and it's largely due to the market share. It has the most people looking at it, the most people are using it. Therefore, for attackers who have criminal interests, it has also the lion's share of potential victims. So, finding a vulnerability or an exploit in a Windows platform could get you a lot more if you were malicious. Next is the massive size of the Windows code, which also includes the hundreds of drivers, most of which are third-party. And these third-party drivers may have no security review on them at all. They obviously don't go through Microsoft, so they don't benefit from any of the secure development lifecycle practices that Microsoft or the OS developer would use. And on another note, several security researchers in the community have gone about investigating how easy it actually is to get a third-party code signing certificate to develop valid drivers for a Windows OS platform. And they found that it's remarkably easy, so much so that it's likely that malware developers are doing it right now, which is a concern. Another aspect of the Windows security problem is it has a lot of backwards compatibility features, a lot of user friendliness. For a while, auto run was a huge security vulnerability for USB drives and CDs and etc. And a lot of other plug and play features that make it essentially, as we call it, target rich. And there's been a more recent development that has been found by essentially reverse engineers in the community that a lot of Microsoft products are directly tied into the kernel functions. Outlook, Internet Explorer, Word, etc. actually make use of more or less undocumented features of the Windows kernel, which is believed allow them to load faster. This kind of makes it so that they can compete in a manner against the load time of competing applications such as Chrome, Firefox, and etc. So let's dive into an overview of Windows Registry. So the registry is essentially a database for information, settings, and configurations for everything. You can edit it with regedit.exe, and the 5 core areas of it are called hives. The HKey class is root, current user, local machine, users, and current config are the 5 top level hives. And these main 5 hives, along with other sub-hives, provide the Windows operating system layers and components everything it needs to know to perform access control, group policy decisions, local security settings changes and rules, permissions, evaluations and changes, and user access control and user rights assignment. Essentially, any form of security setting or check comes through checking the registry. So the top 5 hives are usually visible by default. They're associative arrays that hold typically text, but sometimes just abstract data. Sometimes CD keys is what most people would be familiar with. But more importantly, you should note that they can also store subhives and other forms of collections. HKey class is root. HKey stands for hive key. It's sometimes just shortened down to HK in other notations. Contains all the file type associations. So what files should be opened with what applications. HKey current users contains all the preferences for the currently logged on user, and the main supporting files for that outside of the hive are ntuser.dat and ntuser.dat.log, which logs basically changes to this and other user activity. HKey local machine is one of the most important hive structures in the registry. It works with other hives to store all the information related to software and hardware on the current local machine and security information that pertains to it. Also plug and play information as well as HAL info, otherwise known as hardware abstraction layer information, is gathered here to catalog and enumerate all of the system's hardware. This is one of the primary hives that you will see if you open up the control panel and view the system's hardware and other system properties. It will be pulling data that's been populated inside the local machine hive. Now, it works with the system, software, security, as well as SAM hives to coordinate this information as well for primarily security reasons. And in general, these hives are actually sub-hives of the local machine hive, which is sometimes just known as the HKLM hive. They each have their own corresponding files along with the .log and .sav, um, and they are typically stored in whatever directory maps to the shortcut for system root in the system32/config files. That's typically where you will find all registry files. Now, HK users contains data for every single user that's authorized on the device. This information will also be stored in the SAM, which is the Windows Security Account Manager. And so, similar to Linux, it will contain everything that the operating system needs to know for that user's environment. So, you'll have information on what their desktop settings, resolution, what environment permissions and configuration they should have, as well as default program settings and other network permissions and printers that are allowed to the user. HKey current config contains other PNP information outside of HKey local machine about the system's hardware devices, but this is specially focused on any devices that are utilized during the Windows boot process and startup process. Now, it's important to note that each time a user logs on, a dynamic hive is built under HKey users. It is not statically just saved and reloaded every single time. It is rebuilt every boot. So let's cover the Windows boot process. So the Windows boot process is a lengthy process until Explorer.exe runs and a graphical user environment is provided to the user. And there may be some differences across all the versions of Windows, as well as what hardware there may be. It may be a motherboard with just regular old legacy BIOS, or EFI, or UEFI, which I jokingly tell people is universally exploitable firmware interface. But we're going to cover on the general principles that should hold true in any case. So when the processor boots, when the hardware first boots, it's going to be operating in 16-bit real mode, which effectively means there's no memory permissions or security. Everything is flat, and the processor can access, or at least the code can access, any aspect of memory in the system at this point. So the very first thing that will happen is the power on self-test. The processor isn't necessarily operating at this point. It's checking diagnosis and making sure it's spinning up correctly. The CMOS will check to make sure the clock cycle is operating correctly and do other similar hardware checks to make sure everything is firing off right and everything is good. At this point, afterwards, there will typically be a context switch done by the UEFI or EFI module to load in any other firmware for devices at this point. Afterwards, the MBR is going to be loaded, and for Windows, the boot manager is boot MGR, and this will read any boot configuration data stored in the system. The MBR will point to where to look for this data, and it's typically going to be around where the registry information is going to be located, such as system32/config. And so the BCD store data will tell the boot manager which operating systems are enabled on the device. And in the case of dual boot or multi-boot, if there are multiple OSs allowed, it will display a menu for the user to select which one to proceed booting with. And so if Windows is selected, typically winload.exe is responsible for handling the rest of the Windows bootloader process, and it will be loaded. And winload.exe is at the point where it starts jumping into protected mode, which has basic memory protections, permissions, and etc. Process can't generally access any given part of the memory. There may be barriers, specifically there may be permissions forbidding it, but at this point it's still going to be a single process executing on the processor in most cases. And so it will load the kernel, which in most cases is ntoskrnl or ntosKernel.exe, and that will also load hal.dll for hardware abstraction. And it will load the system registry hive in for two reasons. The first reason is to load any drivers that are already configured for the system into memory at this point, but it doesn't start them just yet. And secondly, to enumerate any new hardware it discovers at this point, so it can begin populating the local machine system hive with this new hardware information. And so, in doing so, it's going to jump back and forth between protected and real mode several times in this process. And so it will next check whether or not the system shut down properly. If it hasn't, it will prompt the user for which way he or she would like to boot it, as well as select the last known good configuration. And afterwards, WinLoad will start the memory paging, so that will be pagefile.sys that is typically responsible for that. And .sys files are drivers for the Windows operating system. And it will then pass control to the kernel itself. So this causes the kernel to take over, and it'll start accessing the API provided by the HAL DLL and start interacting with the other hardware, and all the drivers that have been loaded into memory thus far will thus be essentially activated in this process, and it's going to do all of the initialization for the drivers and the hardware, and use the results of this process to populate the HKey local machine hardware hive. And so after that, it's going to start the critical services and other drivers located in System32 drivers, and it will then start the session manager subsystem. And a lot of the components in Windows after this point are called subsystems, or some form of manager system or manager subsystem for various things. This one is the one responsible for handling all sessions running on a machine, so both in the system session as well as the various user sessions that may be running on the machine. And so this is the point where kernel mode and user mode are differentiated, or in other words, created. And Win32k.sys is a collection of drivers used for instantiating and running the kernel mode, and WinServe DLL and the CSRSS exe are primarily used in initializing the user mode. As far as I know, that nuance I may be wrong about. And so it's going to iterate through a collection in the registry under the HKey local machine system, looking for the current session settings for subsystems, and start initializing any of them that are marked as required during the boot process. So this pertains to environment variables, any virtual memory settings, as well as other things that are required for starting up a user's environment. So smss.exe is a big target for malware because almost every online resource says you should absolutely not terminate it, as it is critical for the stability of your system because it's responsible for maintaining the user and kernel and sessions going on. And so malware often, I've seen tons of malware over the years that names itself, once it gets on the system, smss.exe or variants of that, in order to kind of trick users to think it's not malware, or avoid trying to kill it or deal with it. Another thing to note is the Session Manager subsystem is considered the first native application to start up during the boot process. And it also starts the Win32 graphics subsystem and the client-server runtime subsystem, aka CSRSS.exe, which provides user land applications access to the Win32 subsystems, as well as functionality for handling consoles like the DOS prompt and GUI features, as well as GUI shutdown. And CSRSS is considered the second native application that is started up. Finally, it will start the winlogon.exe executable, which is responsible for handling the logon, which creates other sessions as users log on, and it will then create the services.exe, which is the control manager for other services, as well as the local security authority process, which is lsas.exe. There have been a lot of tools that have targeted LSAS, as well as the security account manager, or SAM, because they store a lot of credential information. Over the years, they've been found in earlier implementations to store the passwords in simply plain text in memory, and they've improved it a bit over implementations to store it in and landman hashes, which again are very crackable, and other forms of hashes. Ultimately, it's a big target nowadays for stealing hashes that can be passed along to other nodes on the domain, or specifically other machines on the Windows domain. Anyways, I digress. The winlogon process executes user init.exe, which begins applying group policy and permission settings to the user's environment and file system, and in that specific user's registry hive. And finally, explorer.exe will be launched, and that is what provides the GUI and the graphical desktop that everyone is used to in Windows. And that is a lot of information, and that's about all you need to know for the Windows boot process for the scope of this class. We're not going to test you on the recite step number 5 of the Windows boot process. So nothing like that is going to happen. It will come up on the homework, but you can use the slides and the video for the reference. The rest of this lecture video is going to be a mix of lecture video from the 2013 iteration of the course, where the content is still correct and relevant. And so you'll notice that the mic quality will change, and there will be an audience question here or there, and some other background noise. And without further ado, it's going to resume right now.
So subsystem startup is started by also the session manager subsystem, and let's get into that. This big ugly graph is from Windows XP in 2000 era. I have another similar one for Vista and 7. At the top you have user mode. Above this line, at the bottom you have kernel mode. All basically user mode systems and services interface with the kernel through two APIs. The first one's the Win32 API. The second one is the NTDLL API. This one is basically closed source and undocumented by Windows, and they provide the Win32 API, which is all these subsystem DLLs, to communicate with the NTDLL, and that handles communicating with the kernel. Basically, it's just a programming interface for how Windows handles everything. So here's the one for current systems, Windows 7 and Vista, and you can see much better in this diagram that all these subsystems, whether it's environmental subsystems, applications, service subsystems, or system process subsystems, they all communicate with the kernel through Windows DLLs. Very rarely do they ever bypass NTDLL. NTDLL usually handles all communications with the kernel for anything in user mode. Question?
So is it common attack to like corrupted DLL?
Yes.
Those are doing communication with the kernel?
Yes. We'll get into rootkit design and how all the horrible things that can happen to Windows actually happen. Yes.
I'm assuming there's an API that NTDLL uses.
Yes, it is.
is it common for malware to bypass NTDLL and try to interact with that API directly?
Uh, Basically, the internal kernel API, just like NTDLL's API is undocumented by Microsoft. It's well documented on the underground. The kernel API, basically system calls and stuff like that, there's sufficient documentation out there because third parties have to program drivers, and they basically have to know how I/O request packets are sent. That's basically when drivers operate, they send packets between each other and processes. Packets don't just really don't extend to the internet. They also apply to the workings of an internal system. Basically, on a motherboard, everything operates on a bus, and that can be seen kind of as like a medium that everyone shares. So they have to share it by sending packets, just like we share connections to the internet. So there has to be sufficient documentation for that, for third parties to develop drivers. But for some of the really core systems, Windows actually goes so far to obfuscate many of the binaries for things, especially for things to protect and harden the kernel. Because once you get a rootkit at some level, you have ring 0 access. We discussed it in the last lecture. A lot of you guys weren't here. Ring 0 access is the highest level access you can have within an operating system. User mode is at ring 3. There are things that exist above ring 0, such as ring -1 and -2, which is basically BIOS and SMM. We might get to that. So if you're operating at ring 0 and you have some sort of control over the system, you can turn off other things that are ring 0, such as system security protections. And we'll get into that. So you can see that NTDL basically handles communication to the system service dispatcher, and basically there's a system call that's an interrupt that's basically sysenter that is called at the assembly level every time there's a switch from user mode to kernel mode, and I'll show you guys that in the rootkit section. And then there's all these managers. There's advanced local procedure call tables. There's configuration manager. There's process manager that handles scheduling and process control. There's the memory manager. And there's the security reference monitors. There's plug and play manager, object manager, and et cetera, et cetera. And then there's the kernel and the hardware abstraction layer. So those Windows DLLs at the top, the subsystem DLLs at the top, those make up the Windows 32 API. They're very well documented. They're provided for people to have just enough information to program basically anything they want on Windows. And that's a better, I guess, diagram showing you exactly what they are. So environment subsystems are interesting. I'm going to go back a couple slides. Here we have environment subsystems. OS2 and POSIX mean basically there are subsystems explicitly for compatibility with OS2 operating systems, or OS2 using operating systems, and POSIX also using operating systems. And here SUA stands for subsystem for Unix-based applications. So there's some sort of support for Unix built into Windows through that subsystem.
So let's take a moment to think about it a different way, because it is all very, very complicated and complex, and there's a simpler way to think of all the subsystem DLLs. And I like to teach it in reference to Office Space. So in that movie, the people on the left are interviewing this guy on the right for his job that he already has. They're re-interviewing him. They're like, so what do you do here? Why should we keep you? And he tells them, I take what the customers want, and I tell it to the engineers. And I take what the engineers want, and I tell it to the customers. It just has to happen this way. And in an operating design sense, that is how it has to happen. Because you can't expect every single application developer who wants to program something for your operating system to learn every single nuance of the operating system internals, especially going across multiple versions. So the NTDLL API and the Win32 API offer a level of abstraction that works across the operating system versions for Windows space. And the secondary benefit of this approach is obviously it provides security through defense in depth. By not exposing the Windows internals for, say, network access, file system access, changing or checking security permissions, it allows for perhaps discrepancies across the Windows implementations from 3.1 to the most recent to not necessarily be exposed to the mishaps or bad coding of applications across the versions of Windows. And that, in a sense, also offers the third benefit of stability.
So this is the breakdown of the 8 categories of functions that are provided by the Windows 32 API. There's not 8 files for the Windows 32 API, but there's 8 basically categories of things that it does. There's the base services for file system handling, handling devices, also processes, threads, and error handling. There's advanced services for dealing with the registry, basically power management as well. There's also service management and user account management. There's graphic device interface functions, basically for handling monitor output, also printers. Then, aside from that, there's the user interface, so Windows buttons, menus, scroll bars, etc. There's also the common control library, which basically handles loading bars, status bars, toolbars, and tabs. It's very related to the user interface library. Then the common dialog box is basically dialog boxes Windows encountered an error. Would you like to send Microsoft some info so we cannot do anything about it? Kind of dialog boxes. Then there's Windows Shell functionality, which handles operating system shell. And that's handled in those DLLs, Shell 32 and Shell WAPI. And then there's finally network services for handling all sorts of things, and that's predominantly Net API 32. But I think the main files break down to the ones that are most commonly used are kernel32.dl. That is not kernel mode DL, that's for user mode. It exports most of the Win32 base API, predominantly memory management, input-output, process handling, and synchronization, and also user 32.dl, which handles exporting functions that create and manipulate the Windows user interface. So let's get to NTDLL. Like I said, it's mostly undocumented by Microsoft, but it's historically been well documented across all versions of Windows. I don't know about 7. I haven't looked into any of that on the underground. The majority of applications do not directly call ntdll.dll. Applications that link or call ntdll directly are called native applications. Native applications cannot be run or started by the user. So smss.exe and csrss.exe, you can't start them up as the user. So if you try to kill them and then restart them, I think it'll just be SOD, blue screen of death. So the vast majority of exported functions by NTDLL's API are prefixed with NT. So you have NT display string, NT read file, and NT write file. So the Win32 API function read file calls NTDL's function NT read file. And likewise, write file calls NTDL's NT write file. It's pretty straightforward. You can imagine why, even though they left NTDL undocumented, it's pretty easy to figure out what's going on because things are so verbosely named. So let's talk about exported functions because this is how APIs are provided, and you probably haven't covered this in any of your classes. Um, exe files and DLLs both have the functionality to export functions to interact with other programs and code. It's very rare for exes to export functions. Sometimes malware does this because it's a very little known feature in portable executable files. And if malware does export functions, they will almost always use intentionally misleading function names. Like read file will actually be like OpenSocket for a listener. Yes?
In a technical sense, aren't exe and DLLs just like there's a flag in the PE header or something, and that's like the major difference between them or something? 'Cause I think they
Yes. So portable executable, this file format has been around for, I think, 20 plus years. The following files are all portable executable files. You have exes and DLLs. Really the difference is, I guess, a flag that differentiates the two, but also they predominantly, on average, have different sections that they use. There's also CPL, OCX, .sys. Like I said, those are kernel mode drivers. .scr, I have no idea what that is. I can't remember what that is. I should know. Anyways, and then DRV, pretty sure that's user mode driver. It contains information as to what functions are also imported as well as exported in its headers. These are contained in call tables. In user mode, it's the import address table, the IAT. I'll get to that in a second. So when reverse engineering portable executables, especially for malware, looking at the functions that it imports is very informative. If you think something's malware and you want to gain more information as to how it behaves, if it imports functions that create files, write files, and read files, you know right there that it may be doing something on the disk. As well as if it has functions that basically open sockets, it may also be doing some network communication. There's also functions that are giveaways for editing the registry, and I have tables for all that. So malware can also play tricks by importing functions by indirect reference. In essence, basically import the 6th function from this DLL. It's not going to basically say import create file W. It's whatever the 6th function happens to be. It could be the 6th function squared divided by 3, something like that. Or offset by a hex address. So when applications are compiled, the API calls do not use hard-coded addresses. So these DLLs, these dynamically linked libraries, when the binary is run, when the application is run, they're linked in when it's running into memory. They're not loaded into the machine code for the application, because if you did that for every single application, the size of applications would probably be 5 megs minimum, because there's so many functions in these DLLs. That's the entire reason why dynamically linked libraries and shared objects came along very early in the computing industry. So since they're not hard-coded addresses, they basically work through a function pointer. They're organized in the import address table, and this way the API call doesn't have to be touched up by the compiler with the correct jump address for the API code. Packed executables are known to mess with the process IAT table to make it smaller, sometimes to cut out unnecessary stuff. So here's some interesting functions that malware may often use. Like I said, functions for creating files, for reading files, for writing files. The second and the third one are interesting. Find first file W and find next file W. Those are actually used for traversing directories. So find the first file in a directory, then file the next, and then find the next, and the next, and the next. Basically iterate through it. And then there's get process heap. and open process. Those are all used for manipulating processes. From user32.dll, the previous one was kernel32.dll. This one is basically for user environment GUI. Even though malware may have GUI manipulation functions, it doesn't mean it's providing a GUI to the user. The GUI could be hidden from the user, yet could have other functionalities that are common in a GUI. The second to last one, set Windows hook XW, is very important. It's for setting things that's, sorry. It's an API call that malware often uses for key logging. It's prominently used in spyware. So it basically creates a hook. I covered hooks roughly last time, but for the half of the class that wasn't here, hooks are basically when you have an entry in the call table, you have the function name and then the address for that routine. If you want to use that function, basically you jump to that provided address in the entry. When you want to hook that, you override it with the address for your hook, and you do you can have some code there, and then you can jump to the original address for that API routine. So basically, it allows you to run some code first, and then run the API call, or not run the API call and just return. Let's see, ADV API 32. I think that stands for Advanced API 32. I don't know why. Some things get named silly things. But every single one of these functions is for editing the registry. So remember how I said the service manager subsystem looks for all the things in that one registry chain that are listed as required subsystems, and then loads them every time on boot. So if something's editing that, they would be using these, that malware would be using these functions. I'm not going to test you on these functions. What does this one do? Even though they're pretty verbosely named. This is all listed for reference in case you guys want to do any malware reverse engineering projects. Shell 32 is mainly for launching other applications. Basically for performing operations on a specified file, to notifying the current application that's calling the second function here, sh change notify. It causes basically that application to be notified every time some event happens. So let's get to security in Windows 7. Over the years, there's been a lot of development. The top 5 things we're going to get to in exploit development, but basically there's data execution prevention, address space layout randomization. There's a GS compiler option, safe SEH, kernel patch protection, and the advanced mitigation experience toolkit, among others. But mainly we're going to get into the user account control. The UAC, that's what some consider the annoying little thing that comes up when you double-click on an exe file that says, are you sure you want to run this? We don't know who published this, or we do know who published this because we can view the certificate and there's the signature for the code that matches. As well as this application wants to open a port through the firewall or make an outgoing connection. Those are examples of the consent prompts. Also prompts for administrator access. The security accounts manager, it is responsible for storing the user's passwords in a hash format. The SAM file is stored in system root system32 config, just like how Linux, we discussed the etc password file and the shadow file. We're going to discuss the landman hash, which was a terrible idea. I don't know who thought of it. Really just a terrible idea. And then the NT landman hash, which came along, which used some more, at the time, more advanced crypto techniques but all the NT-landman protocols for Active Directory have been 100% broken at some point to date, and that's why they now default to Kerberos. So the Windows kernel has an exclusive file system lock on the SAM file to prevent any sort of opening or any sort of copying, basically any sort of file operation while Windows is running. If you want to edit the SAM file, you basically have to boot to some live CD or some other partition, mount that file system, and then edit the SAM file while Windows is not running. In order to basically add salt, or rather more security, the syskey function was introduced, and the algorithm for this is basically the on-disk copy of the SAM file is partially encrypted with the key, called the sys key, and the in-memory version of the SAM is, I'm pretty sure, not. It should be noted that the in-version memory of SAM can be dumped while Windows is running via the PW dump tool, and I'm sure some Metasploit modules. In Windows 2000 and before, if an attacker simply deleted the SAM file, no passwords were required for login. It's just like, okay, everything looks gravy. So I think better desktop auditing is one of the better things that Windows has provided. The logs for Windows are XML based, and all tasks that are running are tied to an event. There's fine-grained support for auditing administrator privileges, so businesses with large IT departments that have a wide amount of employees running as administrator, there's fine-grained log auditing for exactly who's doing what at administrator access. There's also better filtering with this, so it's much easier to filter out the noise and find the events that you want. I say even easier than any Linux system. And there's, in Windows 7, been entirely reworked event viewer. I, however, prefer using Splunk. Splunk is a free tool that basically runs a local web application that provides really nice GUI, really nice chart graphing for system logs, and you can create basically views based on log categories. There's thousands of log categories, and most of them are just taken up by drivers, so you can filter out a lot of noise that way. Another thing in modern Windows system is the network access protection. This is mainly for enterprise systems. Basically, when a new computer connects to the domain, the network access protection system basically checks all of its security policies to make sure that they meet the corporate policy. Basically, the access control policies that are listed in the registry. And also make sure that they are fully patched with the latest service packs and critical updates, and have up-to-date antivirus. Which makes it really great for system administration. Another thing that makes it really great for system administration and attackers is the direct access feature. Is that basically IT departments can, through the GUI, have direct access to any computer on the domain and can take complete control, and it can all happen completely seamlessly to the user. It doesn't necessarily have to dominate the user's mouse and keyboard and everything. The user can keep doing what they're doing, and basically the IT guy gets a second view of the computer, a new desktop and everything else, and can do whatever they want. So if an attacker compromises an IT department's machine, they could use this to pivot into other systems. App Locker is a very good feature. It basically allows for blacklisting, whitelisting applications, and also for enforcing publisher rules based off digital signatures. It helps IT eliminate the unknown and unverified applications in the network, basically keeping your employees from downloading LimeWire and getting your company into trouble, as well as downloading all the malware that comes with that. The rights management service is a fine-grained access control for documents can control whether users want to copy, whether users can copy, print, open, edit, etc. a document. BitLocker is also very important, especially for laptops and even thumb drives. It offers full hard drive encryption and is focused on mainly protecting the OS volume. Though for laptops it's important to have any data volumes also protected with hard drive encryption in case they get lost. Say it's a government laptop and it gets lost and missile codes are stolen. It's not a good thing. It's not as uncommon as you think. Bill Clinton actually lost the card with the football. Does everyone know what the football is? It's a briefcase. It's like handcuffed to a Secret Service member's arm at all times. Basically, eats, drinks, lives, sleeps with it on. I mean, they take turns. But only the president has the access code to open up the briefcase. Well, he sent his suit to the dry cleaners outside of the White House, and he left it in there, and they lost it for, I think, 3 months. Yeah, so I mean, it's not unheard of. If anyone, you could probably Google that pretty easily. I don't need to find it for you guys. So for things like thumb drives, you could lose it and not find out that you've lost it for weeks, and you could have important documents. So BitLocker is a really great Windows standard feature that can lock down thumb drives. And one of the most important things in system administration that we covered previously is least privilege. Least privilege is implemented through basically the access control lists in Windows. In the Linux lecture, we discussed how access control lists are not enabled by default for all users. So the Unix permission model is owner, group, and everyone else. So if you wanted to give specific permissions to one other user, you'd either have to create a group with just you and him in it, or let him own a version of the file. With access control lists in Linux, it allows you to basically specify specific permissions for that other user and for other different groups. It's very flexible. And so likewise, access control lists in Windows are very much the same. Access control entries are basically entries in the access control lists, and they control or monitor access to an object by a specified trustee. Trustee means basically user. So the main entries, the main information in ACE entries are the SID. It's basically the security identifier for the trustee. It's kind of similar to the UID for users in Linux, which is the user ID. There's the access mask. That's very similar to the permissions mask in Unix. So I'm sure you all have seen like chmod 755 some file. Basically the numbers go through 0 to 7, and they specify basically bitwise permissions for user, group, and other. So there's an access mask that specifies the access rights for files, or rather objects. And then there are 6 types of ACE flags. There's flags to dictate which type of entry it is. And then there's sets of flags to dictate whether the access control entry applies to child containers and directories. And this is somewhat straightforward. It's also very important for application development. So I'm going to try and breeze through the rest and get to the good stuff. So domains, workgroups, and home groups. I'm sure you've heard these terms at some point and wondered what's the difference. So all computers running on a Windows network, all computers running Windows on any network must be part of a workgroup or a domain. They can be part of a home group also, but it's not required. It's required for them to be either part of a workgroup or a domain. So in a workgroup, all PCs are peers. No PC has control of another. That's the main things. In order to log on to a different PC, you must have an account on that PC. Home group, Basically, you must belong to a work group as well, so all those permissions, all those requirements apply. The main purpose here is to make it easier to share pictures, music, videos, documents, and printers. Home group is password protected. Work groups are not password protected. But for home groups, you only have to type it in once when you first add it to the home group. So you can reboot many times. You only have to type it in that one time initially. Domains are what we're going to dive into. So, on a domain, one or more PCs are the domain servers, basically the Active Directory servers. Those are controlled by network admins that use the servers to control the security and permissions for all the computers in the domain. Any changes to those policies are automatically made to all the PCs in the domain that are currently on, and as they come online. Password credentials are required every time you log onto a PC in a domain, and if a user has a domain account, then he or she can log on to any PC in the domain. Basically, authentication is handled by one of those domain servers. So, history of the Windows domain is basically Microsoft wanted a way to make everything just work seamlessly together. You plug it into the network and you start sharing, collaborating, etc. Started with LANman, then NT LANman. Database history is mainly what everything ships with now is Active Directory. Servers that run Active Directory, the Active Directory servers are called domain controllers. So that handles the authentication and policy for system administrators. It is predominantly built on top of LDAP, Kerberos, and DNS. And the stuff at the bottom is just old stuff. So, domain connections can be supported over LAN, WAN, or VPN between networks. That makes it a pivoting target. So, here's the history for the security protocols for Active Domain and what happened prior to it. LANman was first. Its hashes were notoriously weak, made it really easy to crack passwords. It still appears in some places, even to date, and even in Apple operating systems. I think Carlos Perez had a good talk, I forget where, on post-exploitation in Apple OS. Basically, you flip a registry flag and it takes the passwords stored in memory and restores them on hard disk in LANman, which is way easier to break than everything else that is used, just for backwards compatibility. Then NT LANman version 1 and version 2 were introduced. Version 2 used HMAC MD5 for authentication, CRC and message digest algorithms for integrity, and RC4 for encryption. And their sessions were very similar to MS Chat v2. All of those acronyms that I said thus far have been broken. That's all you need to know. Ever since Windows 2000, Kerberos has been adopted. Almost out of time, so I'm going to get to the rootkits part and start that next time. That's actually the interesting stuff. So Kerberos has replaced NT LANman as the default authentication protocol for Active Directory for working in a domain. However, NT LANman is used widely and by default in instances where the client cannot access a domain controller. It defaults to NT LANman. So remember, all that stuff has been broken at some point. There have been fixes that have come out to fix some of the problems, but they're built off basically insecure foundations. Also, it defaults to it when it's authenticating to a server using just an IP address. When it is authenticating to an Active Directory for us that has basically backwards compatibility legacy stuff that still uses the NT LANman stuff, and is authenticating to a server that's not part of any domain, or, most interestingly, cannot access Kerberos ports due to a firewall. So if an attacker can change your firewall and disable those ports, it might cause your system to default to the less secure protocol. Question?
What if it was like a non-service, block those like externally?
That's just as easy. You can basically block all the ports and then change the password and shut out the system administrator. Logically, what's going to happen is just going to walk over to the router after about 30 minutes of banging his head on the keyboard and then reset the thing and then be like, hey, my password's not working. I'm just going to hardware factory reset it and then set it back up. So, I mean, yeah, I'm just talking about something that could be used more covertly that can allow you to gain access to systems instead of just to deny everything, which can be more useful for attackers. As something as system administrators and incident responders you have to be aware of. So Windows Firewall is on by default in Windows 7 and post versions. There are different profiles for home, work, and public. It's really interesting because it allows users a lot of flexibility, and it's much easier to configure than IP tables and any GUI-based Linux firewall editor. The most important thing is it ties connections to applications. So it monitors connections that are incoming and outgoing and can require user consent. Basically, the user access control, the UAC consent prompts. Also, another good thing it does is application whitelist.
And so for now, that concludes our lecture on Windows internals. Next time we will pick this topic up again when we cover rootkits. We will be discussing rootkit design and analysis for forensics reasons for both Windows and Linux operating systems. There are many common patterns that attackers use between these two platforms that you may find surprising. So to recap what we've covered so far in this lecture, we started off with how memory is handled, the difference between paging and segmentation. And we went into the registry, the 5 main hives, and which hives are populated upon boot, and also the boot sequence, and covering how the boot sequence jumps between real and protected modes for memory protection, as well as what processes are responsible for starting what, which subsystems and systems do what. And then we dived into the PE file format and other Windows architecture details. And we wrapped it up with Windows security and domain topics, Active Directory, Windows workgroups, home groups, Windows Firewall, and etc.